Bismillahirrahmanirrahim. Uh, I will present the three-phase delta and star configuration from a single-phase winding. In the animation is shown a single-phase generator producing an single-phase AC output. In the next, it's shown that three single-phase are placed red, green, blue, 120-degree electrical apart, and we have the same permanent magnet moved by a single prime mover, means the mechanical input. The three phases, they are connected to the load, and through the neutral we are getting back the return. Similarly, in this one we have the three-phase generator and the three-phase load, and the dotted lines show that at any instant the sum of the three, whether it's a voltage or current, is equal to zero. Now, the basic questions which is usually come to the mind: how three-phase star and delta configurations are developed. The second question: why we use three-phase when we are having a single phase? Where is the difference between these two? We will go through that also. Now, first we will take a single phase generator. Now, the question keep in mind is that generator is which converts mechanical energy into electrical energy. Now, in the circuit diagram, we have been shown the load, and which is connected to the generator, and the generator is connected to the prime mover. Prime mover is a mechanical input, which we call it the mechanical input to the generator. Uh, it could be a hydropower plant, it could be a diesel, it could be any mechanical input. Now, we have two wires. One is L red live wire, and N is the neutral return wire from the generator through the load back to the generator. Now, this is the mechanical input shown here for this single generator. Now, if the load is increased, what will happen is that we have to increase, or we have to connect the load, increasing the load to the another generator. Now, we have connected the second generator. Now, it's a separate mechanical input, a separate generator, and separate a new load. Now, similarly, if we have further increase in the load, so we cannot provide with the same single phase generator, we have to connect the uh, load to the third generator. Now, the question arises that the three-phase single generator run by three prime movers are connected to three loads, each by a pair of live wires with L and neutral. Now, the total are 6 wires used in this case. Now, the question is how to transform the three single-phase generators to a single three-phase generator. Now, in the next slide, we take the same generator, single phase. Mechanical input is not shown here. And similarly, we take the second one, but the phase difference between the first and the second one, if we keep it minus 120 degree, and similarly the third, we keep it 120 degree. Now, if you have this type of production from each of these generators, so we can transform them to a single three-phase generator. Now, we have this configuration. Now, the first red one is at 0 angle, the yellow one is at minus 120 degree, and the third one is blue one is 120 degree positive. Now, operate the three generators with a defined phase angle between the voltage wave in each generator by 120 degree. Easily we can make a configurations star and delta configuration. Now, in the next slide, we'll take all these three generators with 120 degree electrical apart, and we will connect them in Y and delta connection. Now look at this. We have taken the same generators. Now we have the VR, V yellow, and V blue. We can connect the neutral of the red with the yellow, and then again we connect the yellow with the blue. Now we have connected all the three neutrals together, and we are left with the VR, VY, VB, mean the phase cape line. Now, if we take the first red one as it is, and if we take the blue as it is, and if we take the three as it is, means the red show the live wire, yellow show the VY show the live wire of the yellow, and VB show the live wire of the B. Now, if we connect these neutral together as we have done in the this diagram, so in this way we get the star connection. So instead of having three separate single phase generator run by three prime movers, now we can have a one single three-phase generator by connecting the three phases 120 degree electrical apart. Now, so now we have a single generator. Right. Now, what is the difference between the three single-phase generator and the three-phase generator? So in the three single-phase generators, we have three prime movers and six conductors, and are very expensive. Compared to this, if we take a three-phase generator, then we have only one prime mover and we have three conductors without neutral. We will discuss about that. So definitely there's a change in cost. Now, so this is a three-phase. It will be connected to the load. Load is not shown here on the main diagram. Now, next we take the delta connection. That how we connect the delta connection. So we take three-phase generators, 120-degree electrical apart, and we can connect VR with a neutral of V blue. And similarly, we take the phase of yellow and we connect it to the neutral of the red. And similarly, we take the blue and connect it to the neutral of the yellow. Now, if we take these three diagrams separately, like this one, the red one, if we take it, and we have a negative and we have a positive, the red one is positive shown and the Y. So similarly, if we do the same connections here as we have done it here, right? So we can look at it. This is the yellow one. This is a blue one. And if we connect them as we have done in the this diagram, so in this way we have connected the three single phase to a single three-phase generator. Instead of having three prime movers, we have connected them, right? So uh, if the balanced load is applied to the three-phase in this case, so the total sum of the voltages will be equal to zero. Similarly, if it is unbalanced, then the total current will not be equal to zero, or the voltage will not be equal to zero. So in that case, the additional current will flow within the delta winding. So usually we keep the delta windings with a balanced load. But in case of the star connection, in the previous case, we have a neutral. So if the load is unbalanced, so the current will flow through the neutral. Now, now the question is next, how three-phase configurations is possible, you know? If we keep them 120-degree electrical apart, right, this one, so you can look at the mathematics of it, that if we further expand the equations, so the total sum of the three will be equal to 0, provided they have the same magnitude. Means if they are connected to the same load, or mean the load have the same impedance, or the voltage in three phase are the same, the current in three phase are the same, so we will have 0. In this case, if we take this one at 90-degree single phase, excuse me, so we can see that the phase 1 is at maximum of 1, could be current, could be voltage, and the other two, they are at minus zero point 0.5. So if we sum of these three, we make the sum of these three, it comes out to be 0. So at any instant, the sum of the voltage, and that's the reason that we can connect, in case of uh, Y connection, we can connect them to neutral, because at any instant, at the point of the neutral, the voltage is equal to 0. And similarly, in the delta, we connect the live with the neutral. So at any instant, live and neutral, at that particular instant, they have the same voltages or the zero current. So that's the reason we can connect them so easily. Now, how three-phase star configuration is possible, you know. So this is shown here, that we have shown here that how the current is equal to 0 when it's balanced, and how the current is not equal to 0 when it is unbalanced. So that unbalanced cannot flow through the neutral. So in that case, we have to have the neutral wire, you know, in case of the Y connection. But in delta, we cannot have the neutral wire. So in case of unbalanced, the current flows through the neutral. But in case of delta connection, the current, there is no neutral, so the current will circulate within the delta winding. So this is the relationship between shown here, the voltage, and uh, you can have a look at it further, right? It's very clear. Similarly, with the delta connection, in this case, the phase voltage is equal to the line voltage. In the previous case, the line current and the phase current are the same. In this one, the phase voltage and the line voltage, they are the same. And the sum of the three voltages at any instant is equal to 0. right? So here again, due to the unbalanced load, as there is no neutral, what happened to the difference of phase currents due to difference voltages, The difference in voltages, the extra current circulate in delta windings and dissipate across the delta resistance in windings. Hence, the delta winding is preferred for balanced loads to avoid circulating currents. And also in case of harmonics, uh, the harmonics current also circulate within this and it is lost, is not sent to the secondary side. Advantages of three-phase system, a greater power density than a single phase, right? So definitely lower cost and balanced load, the three-phase in balanced load scenario where each phase experience the same load, the sum of the currents in any two conductors at any time is equal to the current in the third conductor that we have already discussed, Also, three provides a rotating magnetic field that can enable induction motor, three-phase induction motor, to self-starting. This is the very main advantage of it, that we make the three-phase induction motor as a self-starting. The single-phase induction motors, which we have usually in the ceiling fans, they are not self-starting. We have to make a special mechanism for that so that we can have a sort of a rotating flux. So we dodge it, instead of single phase, we make it two phases so that we can have a rotating flux. But in the three phase, we can have the three resultant flux. If you look at the red or the black one here, the black one, at any instant, the sum of the three voltages will be equal to the resultant voltage, which is 1.5 times the maximum value of any of the three phases. So in this case, we have a rotating flux, and definitely for the induction motor, we need to have a rotating flux. So when we connect the three phase to the stator winding, so we get a similar type of rotating flux, which induce the flux into the rotor bars of the induction motor, which are shorted. Because of that, the current flows, and because of the current flux flows, so we get two fluxes. One the rotating flux in the stator and the other flux in the rotor. Because of the interaction of these two, the rotor of the induction motor start rotating in the direction of the synchronous flux. Now, the other main advantage of the three-phase and single phase is that if we rectify the single phase, we get a sort of a pulsating output power, DC power. But if we rectify the three phase, right? If we rectify the three phase, in that case, if you look at the red part of it, total, so we get a set of sort of a smooth power output. In single phase, we get a pulsating output, and in three phase, we get a sort of a almost smooth power, except with these ripples, So as these ripples are high, so they can be easily filtered out as in the three phase. So that's the reason that in the three phase rectifier, we can easily filter out the ripples as compared to the single phase. In the single phase, we need to have a high value capacitor. So in order to filter out the filters with a high magnitude. So in this case, we have a high magnitude ripples, but in this case, we have a small ripples. In each cycle, we have around about 6 pulses. So it is easy to filter out. Now, this is the phase color coding of different countries for the red, yellow, and blue, and the neutral. It is shown here, right? And similarly, I've shown here that the how the if you look at it, the primary is connected to the delta and the secondary is connected to the star, because of the reason that the delta, we usually balance a three phase on the star side. So if they are balanced on the star side, definitely, the primary side delta is balanced and there will be no circulating current in the delta winding. This type of arrangement where we have a 400 hertz, usually when the load is near to the transformer. Now in this case I have shown 440 volts, again the same. We have a neutral here. This type of arrangement, 440, when the load is far away from the uh, transformer. So in order to cater for the line voltage drop. Now this 400 volts is the terminal voltage of the transformer. Similarly, 440 volts is the terminal voltage of the transformer. So when it reaches to the load, definitely we have some voltage drop in the transmission line. So finally we get around 220. So we come to the end of